Is our entire existence just a blink? Tonight, we're going to explore why a human lifetime isn't nearly enough to reach even the closest stars. You've probably looked up at the night sky and wondered about visiting those distant points of light. But here's what most people don't realize. The scale of space is so vast that our entire civilization represents barely a moment compared to the time needed to reach our stellar neighbors. By the end of this journey, you're going to understand exactly why the universe operates on timescales that make human ambitions seem impossibly small. Before we dive in, if you enjoy these cosmic explorations, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a real difference for me. Get comfortable. This will be humbling. Picture a child pressed against an airplane window watching clouds drift past below. To that young mind, those billowy white formations look close enough to touch, close enough to step onto if the plane door could somehow open. The child doesn't know those clouds are actually kilometers away, floating in thin air that would steal breath from human lungs. That same child, lying in bed at night, stares up at the ceiling where glow-in-the-dark stars create a miniature cosmos. In the innocent logic of childhood, if you could just build a ladder tall enough, if you could just climb high enough, surely you could reach up and pluck those real stars from the sky like fruit from a tree. This is how our minds work. This is how your mind works right now. Our intuition about distance was shaped by the landscapes where we evolved. You see a mountain on the horizon, and yes, it looks far away, but you also know somewhere in your bones that you could walk to that mountain. It might take a day, maybe two, but your feet could carry you there. You could drive to it in your car in a matter of hours, watching it grow larger through your windshield until suddenly you're winding up its slopes. Think about your daily experience with distance. 10 kilometers feels substantial when you're walking. That's a few hours of steady movement, enough to work up a sweat, enough to feel accomplished when you arrive. But 10 kilometers in a car? That's maybe 8 minutes on a highway, nothing at all. You barely have time to choose a song. These human scales work because everything in our earthbound world fits comfortably within the boundaries of human experience. The farthest you can see on a clear day is maybe 30 or 40 kilometers to the horizon. The tallest mountain you've probably seen rises a few kilometers into the sky. Even our most ambitious journeys, flying across continents, sailing across oceans, these adventures unfold over distances measured in thousands of kilometers and durations measured in hours or days. Now, step outside on a clear night and look up. To your eyes, to your intuition, shaped by terrestrial distances, those stars appear to be points of light hanging at roughly the same distance, like street lamps, like Christmas lights strung across a dark ceiling. Your brain, evolved to judge the distance to predators and prey, to water sources and shelter, tells you that all those lights are basically over there, somewhere up in that dark dome. But let's start with something familiar. The moon. Our closest neighbor in space, that pale disk you've watched rise over rooftops thousands of times, sits 384,400 kilometers away from Earth. Let me help you feel what that distance really means. If you could walk to the moon the way you walk to the corner store, if there were somehow a path stretching through space that your feet could follow, you would need to walk continuously without stopping to sleep or eat or rest for approximately 9 years. 9 full years of walking, step after step after step, just to reach that familiar silver disc. Think about where you were 9 years ago. Think about how much your life has changed since then. All of that time, all of those experiences, all of that growth and change, that's how long you'd be walking through the vacuum of space just to touch the moon. Or maybe walking seems too slow. Let's say you could drive to the moon at highway speed, a steady 100 kilometers per hour, the kind of speed that feels fast when you're passing through countryside. At that pace, never stopping for gas or food or sleep, you would reach the moon after 160 days of continuous driving. That's more than 5 months. 5 months of your life spent behind the wheel heading toward that pale light. This is just to reach the moon. The moon, which you can cover with your thumb when you hold it at arm's length. The Apollo 11 astronauts traveled much faster than any Earth-bound highway speed. Their command module reached velocities of 40,000 kilometers per hour as it crossed the void between Earth and Moon, even at that tremendous speed. Faster than anything you'll ever experience in your lifetime, the journey still required 3 full days. 3 days of hurtling through space in a metal capsule, watching Earth shrink to a blue marble and the Moon grow from a distant light to a world. Now, what if we want to visit our nearest stellar neighbor? Proxima Centauri, the closest star to our Sun, lies 40 trillion kilometers away. 40 trillion. Let me say that again more slowly. 40 trillion kilometers. Your mind immediately starts trying to process that number. But here's the thing. It can't. Your brain simply wasn't designed to comprehend numbers of that magnitude. Mine wasn't either. 40 trillion is so far beyond human experience that it might as well be infinity. Think of it this way. A trillion represents 1,000 billion. But that still doesn't help much, does it? Let me try another approach. If each kilometer to Proxima Centauri were represented by a single grain of sand, you would need several Olympic-sized swimming pools completely filled with sand to represent that distance. Imagine standing beside those pools, looking at millions upon millions of tiny grains, each one representing a 1,000-meter journey. Now, let's go back to driving. Remember that comfortable highway speed of 100 kilometers per hour? If you could somehow drive to Proxima Centauri at that speed, never stopping, never slowing down, your journey would take 43 million years. 43 million years. When your journey began, there would be no humans on Earth, no cities, no agriculture, no written language. Early primates would be swinging through ancient forests that no longer exist. Mountains would rise and fall. Continents would shift. Species would evolve, flourish, and vanish entirely while you continued driving through the darkness between stars. Even traveling at the incredible speed of Apollo 11, 40,000 kilometers per hour, you would still need 108,000 years to reach Proxima Centauri. 108,000 years. The entire span of recorded human history, from the first cave paintings to the smartphone in your pocket, represents less than 10,000 years. Your journey to the nearest star would take more than 10 times longer than all of human civilization. But we have built something faster than Apollo 11. Voyager 1, launched in 1977, is currently the fastest human-made object ever created. Right now, as you read these words, it's racing through interstellar space at 61,000 kilometers per hour. Voyager 1 has been traveling for 47 years, nearly half a century. It left Earth when your parents or grandparents were young. It has traveled so far that it's now 165 astronomical units from the Sun. An astronomical unit, that's the distance from Earth to the Sun, roughly 150 million kilometers. So Voyager is currently about 24 billion kilometers from home. 24 billion kilometers sounds impressive. It is impressive. It represents the farthest any human creation has ever traveled. But here's the sobering reality. That enormous distance represents only 0.06% of the journey to Proxima Centauri. Not 6%, not even 1%, 0.06%. At its current speed, Voyager 1 would need another 73,000 years to reach our nearest stellar neighbor. 73,000 years. 73,000 years ago, humans were still living in caves, still painting on stone walls with crude pigments made from crushed berries and charcoal. They were crafting the first primitive tools, learning to control fire, speaking in languages that have been lost for millennia. Everything you think of as human civilization, cities, mathematics, philosophy, art, science, the entire accumulated knowledge of our species, all of that has developed in less than 10,000 years. The journey to Proxima Centauri would take more than 7 times longer than the entire history of human progress. And even light, the fastest thing in the universe, traveling at 300,000 kilometers per second, even light requires 4.2 years to make the journey from Proxima Centauri to Earth. When we look at that star through our telescopes, we're not seeing it as it is right now. We're seeing it as it was more than 4 years ago. The light that touches your retina tonight began its journey when you were a different person, living a different version of your life. If Proxima Centauri were to explode this very moment, releasing more energy than our sun will produce in its entire 10 billion year lifetime, we wouldn't know about it until 2029. A radio signal sent from Voyager 1, traveling at the speed of light, the absolute speed limit of the universe, takes 23 hours to reach Earth. Nearly a full day for our messages to cross that gap. In November 2026, Voyager will be exactly 1 light day away from us. 1 day's worth of light travel. But even that incredible distance is nothing compared to the 4.2 light years that separate us from our nearest stellar neighbor. Your entire life, 80 years if you're fortunate, a century if you're extraordinarily lucky, represents the tiniest blink in the timeline of the cosmos. In the time it takes light to travel from Proxima Centauri to Earth, you could graduate from college, build a career, fall in love, raise children, and watch them grow into adults. We are creatures built for decades trying to comprehend distances that require millennia. And that's exactly the heart of our predicament. A decade, 10 years, represents 1/8 of the average human lifespan in the developed world. Think about that for a moment. 1/8. In the span of a single decade, you can watch a baby take its first breath, learn to crawl, speak its first words, take those wobbly first steps, and transform into a curious child asking endless questions about the world. All of that miraculous development, all of that learning and growth happens in just 3 years. Those first 3 years of human life contain more transformation than most adults experience in the following 30. A helpless infant becomes a walking, talking, thinking little person with preferences, fears, jokes, and dreams. They learn to recognize faces, to trust, to communicate their needs. They discover that objects continue to exist even when hidden from view. They begin to understand that other people have thoughts and feelings different from their own. 3 years. In cosmic terms, that's less than the blink of an eye. Then consider the journey from childhood to adulthood. The transformation that occurs between 12 and 19, those 7 years that feel both eternal and fleeting when you're living through them. A gangly, uncertain adolescent becomes a young adult making decisions about careers, relationships, their place in the world. Physical growth accelerates and then stops. The brain rewires itself, forming new connections while pruning others. Personality solidifies, independence emerges. 7 years. Less than 1/10 of a human lifetime. During those 7 years, a young person might learn to drive, graduate from high school, perhaps complete their first years of university. They fall in love for the first time, experience heartbreak, discover passions they never knew existed. They begin to see their parents as flawed human beings rather than omniscient authorities. They start making choices that will shape the rest of their lives. All of this profound transformation compressed into 7 short years. An entire professional career can be built and consolidated in 30 years. Think of someone starting their first job at 22, fresh from university, uncertain and eager. They arrive early, stay late, make mistakes, learn from them. They gradually develop expertise, earn promotions, take on greater responsibilities. By 32, they might be leading small teams. By 42, they could be managing entire departments. By 52, that same person might lead an organization, have mentored dozens of younger colleagues, have seen entire industries transform around them. 3 decades of dedication, of learning, of gradually accumulating expertise and wisdom. In those same 30 years, they might meet their life partner, get married, buy a home, have children, watch those children grow up, and leave home to start their own adult lives. They experience the death of their own parents, inherit family traditions, become the older generation themselves. 30 years can contain multiple lifetimes' worth of experiences and growth. Grandparents witness something even more remarkable. They watch their grandchildren grow from helpless infants to independent adults, often seeing them graduate, find love, start families of their own, all within 20 or 30 years of observation. A grandparent might hold a newborn grandchild and, if they're fortunate enough to live into their 90s, might later hold that same person's newborn child. Within a single generation, they watch the future of their family unfold and take shape, seeing their own legacy extend into the future. Our entire perception of progress, of meaningful change, is anchored in these human scales. We think in terms of months for projects, years for goals, and at most a few decades for the truly ambitious undertakings. A month feels substantial for a work project. A year feels like enough time for major life changes. A decade feels like an era. And this isn't just personal. This pattern repeats throughout human achievement. The Empire State Building, that towering symbol of human ambition and engineering prowess, was constructed in just 1 year and 45 days. From an empty lot in Manhattan to a 381-meter skyscraper piercing the clouds, less than 2 years. 3,000 workers labored in shifts around the clock. Steel beams rose at the rate of 14 floors per day. What had seemed impossible became reality in the span of time it takes a child to learn to walk and talk. The Second World War, which completely redrew the geopolitical map of the world, lasted 6 years. 6 years that saw the rise and fall of empires, the liberation of continents, the dawn of the atomic age. Nations that had existed for centuries vanished. New countries were born. Technologies that had been theoretical became terrifyingly real. The world of 1939 was unrecognizable by 1945. 6 years changed everything. The commercial internet has existed for only 30 years, yet it has fundamentally transformed how our entire species communicates, learns, works, and entertains itself. In 1993, most people had never heard of the World Wide Web. By 2023, it's impossible to imagine modern life without it. Within 3 decades, we went from a world where knowledge was confined to libraries and encyclopedias to one where the sum of human information sits in our pockets. Smartphones themselves have only existed for 17 years. 17 years. The first iPhone was released in 2007. Since then, they've become such integral extensions of our minds and bodies that billions of people feel genuinely lost without them. In less than 2 decades, we've created devices that would seem like magic to our ancestors, and we've made them so commonplace that children take them for granted. Social media platforms that now connect billions of people have existed for even shorter periods. Facebook launched in 2004, Twitter in 2006, Instagram in 2010, TikTok reached global prominence only around 2018. In the space of 15 to 20 years, these platforms have reshaped how humans form relationships, share information, and understand themselves. In a single human lifetime, we routinely witness the birth and death of technologies, the rise and fall of cities, sometimes even the emergence and collapse of entire nations. We see the world change dramatically around us, and we adapt, and we consider this the natural pace of progress. Someone born in 1920 witnessed the advent of television, jet aircraft, computers, the internet, and smartphones. They saw humanity go from barely being able to fly to landing on the moon. But when we lift our eyes to space, when we try to apply these human time scales to cosmic distances, everything breaks down. Voyager 1 has been traveling for 47 years, longer than many people have been alive, and it has barely left the gravitational neighborhood of our sun. After nearly half a century of journey, after crossing more than 24 billion kilometers of space, it has only just begun to taste true interstellar territory. 47 years. That's longer than the entire digital age. It's longer than the space program itself. When Voyager launched in 1977, personal computers didn't exist. The internet was a military research project. Cell phones were the size of briefcases and cost as much as cars. In the time Voyager has been traveling, humanity has experienced multiple technological revolutions, yet Voyager has only just reached the edge of our solar system's influence. You see, the sun doesn't just pull on planets with its gravity, it also creates a vast bubble of charged particles and magnetic fields called the heliosphere, our solar system's protective envelope that shields us from the harsh radiation of interstellar space. This invisible bubble extends roughly 120 astronomical units from the sun. To put that in perspective, if Earth's orbit were the size of a dinner plate, the heliosphere would extend about 30 meters in every direction. Voyager 1 crossed the boundary of this heliosphere in 2012, making it the first human-made object to enter interstellar space. Headlines around the world proclaimed that we had finally reached the stars. But being in interstellar space doesn't mean being close to stars. It simply means being beyond the immediate influence of our own star. The Oort cloud, that vast spherical shell of icy comets that marks the true edge of our solar system's gravitational influence, begins at approximately 2,000 astronomical units from the Sun and extends to perhaps $100,000 AU. At its current speed, Voyager 1 will reach the inner edge of the Oort cloud in roughly 300 years. When Voyager reaches the Oort cloud, everything about human civilization will have changed beyond recognition. The United States will be older than the Roman Empire was when it fell. The English language will have evolved beyond our current understanding. Technologies we can't begin to imagine will have risen, flourished, and become obsolete. Entire civilizations might have emerged and vanished. And Voyager will have only reached the beginning of the Oort cloud. Crossing completely through the Oort cloud would require another 30,000 years of continuous travel. 30,000 years ago, humans were painting on cave walls and had not yet invented agriculture. We were nomadic hunters and gatherers, following herds across landscapes that would be unrecognizable today. The pyramids of Egypt, ancient as they seem to us, wouldn't be built for another 27,000 years. Our species, Homo sapiens, has existed for only about 300,000 years. In all that time, through ice ages and migrations, through the development of language and tool-making and agriculture and cities and science, we have never sent anything farther than Voyager's current position. And Voyager has only just begun its journey into the true vastness of space. Our life expectancy has doubled in the last century, from about 40 years to 80 years on average. This represents one of humanity's greatest achievements, the result of advances in medicine, nutrition, sanitation, and public health. A person born in 1920 could expect to live to about 45. Today, a person born in a developed country can reasonably expect to see their 80th birthday, perhaps their 90th. Jeanne Calment, the longest-lived person in verified history, reached 122 years before passing away in 1997. She was born in 1875, when horses and carriages filled the streets and electric lighting was a novelty. She lived to see automobiles, airplanes, radio, television, computers, and the internet, Even her extraordinarily long life, spanning nearly a century and a quarter, would be insufficient time to witness any meaningful progress in interstellar travel. Consider the mathematics of generations. A typical human generation, the time from birth to reproduction, lasts about 25 years. Building the great medieval cathedrals required multiple generations working in sequence. Master craftsmen would begin construction knowing that their sons and grandsons would complete the spires. These projects spanned centuries, passing from father to son to grandson, each generation adding their skills to a vision that extended far beyond any individual lifetime. Notre Dame de Paris took nearly 200 years to complete. Cologne Cathedral required over 600 years from groundbreaking to final completion. These monuments to human faith and ambition required the dedication of 20 to 30 generations. Each generation of craftsmen learned from their predecessors, improved techniques, and passed their knowledge to their successors. But traveling to Proxima Centauri at our current technological capabilities would require 3,000 consecutive generations. 3,000. That's more generations than have passed since humans first began cultivating crops in the Fertile Crescent of the Middle East. Agriculture began approximately 12,000 years ago. In the span of those 12 millennia, humans accomplished everything we consider civilization: the construction of cities, the development of writing, mathematics, philosophy, art, the Industrial Revolution, the Information Age, the Space Age itself. All of human progress, every advancement from stone tools to quantum computers, has occurred in less time than a journey to our nearest stellar neighbor would require. Think about this carefully. Every Egyptian pharaoh, every Roman emperor, every medieval king, every Renaissance artist, every Industrial Revolution inventor, every modern scientist, the entire parade of human achievement stretching back to the dawn of recorded history, represents fewer generations than would be needed for a single journey to the closest star. This is why decades feel long to us. Because we live within them. Because our minds, our hearts, our sense of meaning and purpose are calibrated to these human timescales. A decade is long enough to master a skill, to build a relationship, to raise a child, to see your neighborhood change, to watch technology evolve around you. 10 years contains enough experience to fill a lifetime of memories. But the cosmos operates on entirely different scales. It thinks in millennia, in millions of years, in billions of years. Stars are born, burn steadily for billions of years, then die in explosions that seed space with the materials for new worlds. Galaxies slowly rotate, their spiral arms sweeping through space over hundreds of millions of years. The universe is patient in a way that no human can truly comprehend. And when we survey our actual progress into this vast cosmos, the picture becomes both inspiring and humbling. Our solar system represents our cosmic neighborhood, the space where the sun's gravity reigns supreme, holding planets, asteroids, and comets in their eternal dance. It's our local bubble of warmth and light in the cold darkness of interstellar space. Let me walk you through our neighborhood, starting from the center and moving outward. Mercury, the innermost planet, races around the Sun at a distance of 58 million kilometers. Even at this relatively close range, the journey from Earth to Mercury would take months with our current technology. Venus, our hothouse neighbor shrouded in sulfuric acid clouds, orbits at 108 million kilometers, still within what we might call our immediate cosmic vicinity. Mars, the red planet that captures our imagination and fuels our dreams of becoming a multiplanetary species, sits 228 million kilometers from the Sun at its average distance. When Mars and Earth are at their closest approach, which happens roughly every 2 years, they're still separated by about 55 million kilometers. That's more than 140 times the distance to the Moon. Then we encounter the gas giants, those massive worlds that dwarf our terrestrial planets. Jupiter, the king of planets with its swirling storms and dozens of moons, completes its orbit at 778 million kilometers from the Sun. Saturn, adorned with its magnificent ring system, orbits at 1.4 billion kilometers. Uranus, that tilted ice giant spinning on its side, lies 2.8 billion kilometers away, while Neptune, the windiest world in our solar system, circles the Sun at 4.5 billion kilometers. Even Pluto, demoted to dwarf planet status, but still beloved by many, reaches distances of up to 7.4 billion kilometers from the Sun during its elongated orbit. These are the boundaries of what we traditionally consider our planetary neighborhood. Now, here's something that might surprise you. Every single human being who has ever lived has spent their entire existence within 420 kilometers of Earth's surface. Every human mission, every astronaut, every space traveler has remained confined to what we call low Earth orbit. The International Space Station, that marvel of international cooperation orbiting overhead, circles Earth at an altitude of just 420 kilometers. To put that in perspective, if you could drive straight up at highway speed, you'd reach the ISS in about 4 hours. If Earth were shrunk to the size of a basketball, the space station would orbit at a distance of roughly 1 centimeter from its surface. The farthest humans have ever traveled from Earth was during the Apollo missions to the Moon. Apollo 11 carried 3 brave souls a distance of 384,400 kilometers, our species' most distant journey. Between 1969 and 1972, exactly 12 human beings walked on the lunar surface. 12 people out of the billions who have ever lived have stood on another world and looked back at Earth hanging in the black void. Since December 1972, when Apollo 17 returned home, no human has traveled beyond low Earth orbit. For more than 50 years, we've remained close to home, circling our planet at that same comfortable distance of a few hundred kilometers. This isn't to diminish the incredible achievement of human spaceflight or the scientific value of our orbital activities. But when we're honest about our progress into the cosmos, we must acknowledge that we've barely taken our first steps beyond our front door. Our robotic ambassadors, however, have ventured much farther. These mechanical explorers have visited every planet in our solar system, and their journeys represent humanity's farthest reach into space. Pioneer 10 and 11, launched in the early 1970s, were the first spacecraft to journey beyond the asteroid belt and visit the outer planets. Pioneer 10 flew past Jupiter in 1973, while Pioneer 11 visited both Jupiter and Saturn, providing our first close-up views of these distant giants. The Voyager missions, launched in 1977, took advantage of a rare planetary alignment that occurs only once every 176 years. Voyager 2 remains the only spacecraft to visit Uranus and Neptune, conducting historic flybys that revealed these ice giants in stunning detail. Those images of Neptune's deep blue atmosphere and Uranus's strange tilted orientation. They came from a single robotic scout, billions of kilometers from home. More recently, the New Horizons mission flew past Pluto in 2015, revealing a world far more complex and beautiful than anyone had imagined. The images of Pluto's heart-shaped plain and its surprisingly diverse geology transformed our understanding of the outer solar system. But even these heroic journeys, spanning decades and crossing billions of kilometers, represent baby steps when compared to true interstellar distances. Voyager 1, after 47 years of travel, has reached a distance of approximately 24 billion kilometers from the Sun. 24 billion kilometers. That sounds impressively vast until you realize that Proxima Centauri lies 1,600 times farther away. If the distance to Voyager 1 were represented by a single step, then reaching Proxima Centauri would require a walk of more than 1,600 steps, roughly 1.5 kilometers. We've recently built something even faster. The Parker Solar Probe, launched in 2018, is designed to dive closer to the Sun than any previous spacecraft, using gravity assists from Venus to reach unprecedented speeds. During its closest approaches to our star, Parker reaches velocities of up to 720,000 kilometers per hour, making it the fastest human-made object ever created. 720,000 kilometers per hour. At that blistering pace, you could fly from New York to Los Angeles in about 6 minutes. Yet even at this extreme velocity, the Parker Solar Probe would require 7,200 years to reach Proxima Centauri. 72 centuries. That's longer than all of recorded human history. When the Parker Solar Probe finally arrived at Proxima Centauri, the civilizations that launched it would be as ancient and mysterious as Sumerian cuneiform tablets are to us today. Some visionary projects propose even more ambitious approaches. Breakthrough. Starshot envisions tiny spacecraft no larger than postage stamps, equipped with lightweight sails that could be accelerated by powerful laser arrays on Earth. By focusing intense laser light on these ultra-light probes, the project aims to accelerate them to roughly 20% of light speed. At 20% of light speed, 60,000 kilometers per second. These microscopic scouts could reach Proxima Centauri in approximately 20 years. 20 years sounds almost reasonable until you consider what these probes would actually be. They would weigh just grams, perhaps less than a coin in your pocket. They could carry no more than a few simple instruments, maybe a camera, a basic spectrometer, perhaps a radio transmitter. They couldn't slow down upon arrival, couldn't orbit the target star, couldn't land on any discovered planets. They would simply streak past at tremendous speed, gathering whatever data they could in the brief moments of their flyby. And most importantly, they could carry no humans. Transporting human beings requires mass, substantial mass. People need food, water, air to breathe, protection from radiation, space to move around, exercise equipment to prevent muscle atrophy, medical supplies for health emergencies. The International Space Station, which comfortably houses 6 people, weighs 420 tons. 420 tons. That's equivalent to about 300 cars, or 80 elephants, or 2,000 adult human beings. All of that mass is required to keep 6 people alive and healthy in the relatively safe environment of low Earth orbit, where they can be resupplied every few months by cargo missions from Earth. Now, imagine scaling that up for an interstellar journey. A voyage to Proxima Centauri would last decades or centuries. There would be no possibility of resupply, no emergency rescue missions, no return to Earth for medical treatment. Everything needed for the entire journey would have to be carried along from the beginning. The engineering challenges become almost incomprehensible. How do you store decades worth of food without spoilage? How do you recycle water and air with perfect efficiency over decades? How do you repair critical systems when replacement parts must be manufactured on board? How do you maintain social cohesion and mental health during a journey that might outlast the natural lifespan of the original crew? Consider that the space station, with all its life support systems, solar panels, and habitation modules, already represents one of the most complex machines ever built. Constructing something capable of supporting human life for an interstellar journey would require engineering advances that we can barely imagine. The spacecraft would need to be self-sufficient on a scale never before attempted. It would need closed-loop life support systems that recycle everything with near-perfect efficiency. It would need manufacturing capabilities to produce replacement parts and tools. It would need agricultural systems to grow food continuously. It would need medical facilities to treat injuries and illnesses that might arise over decades. And all of this complexity would need to function flawlessly while traveling through the harsh environment of interstellar space, bombarded by cosmic radiation far from the sun's protective influence. The mass requirements alone pose seemingly insurmountable challenges. An interstellar spacecraft capable of supporting human life might need to weigh thousands of tons, perhaps tens of thousands of tons. Accelerating such massive structures to the speeds necessary for reasonable travel times would require energy sources that make our most powerful rockets look like toy fireworks. This is the reality of our current situation. We've built remarkable machines that have explored every world in our solar system. But we remain biological creatures adapted for one small planet, confined by the fundamental constraints of mass, energy, and time. Our greatest achievements in space exploration have carried us no farther than our cosmic front yard. When we measure our progress against the true scale of the galaxy, we discover that despite all our technological advances, despite our dreams of exploring the stars, we've barely begun the journey. And this leads to an obvious question: why don't we simply build faster rockets? Your intuition probably suggests that space travel is fundamentally an engineering problem that could be solved by constructing more powerful engines, bigger rockets, more fuel, higher velocities. Surely these would carry us to the stars. It seems logical. After all, we've been steadily improving transportation for centuries, from horses to steam trains to jet aircraft. Each breakthrough delivered dramatically higher speeds. Chemical rockets, the workhorses that have carried every human mission into space, operate on a beautifully simple principle. They burn fuel and eject the hot gases at high velocity, pushing the spacecraft forward through Newton's third law. These engines can achieve exhaust velocities of several kilometers per second, which sounds impressively fast until you consider the distances involved. The Saturn V, the most powerful rocket ever successfully operated, remains a monument to human engineering ambition. Standing 110 meters tall and weighing 2,900 tons when fully fueled, it consumed propellant at a staggering rate of 15 tons per second during launch. Picture that. Every single second, this mechanical monster burned through 15,000 kilograms of fuel, equivalent to consuming 20 cars worth of mass every second. Yet even with this incredible power, even with all that fuel burned at such tremendous rates, Apollo 11 still required 3 full days to cross the 384,400 kilometers to the Moon. 3 days to reach our nearest neighbor, which represents less than 1% of the distance to Proxima Centauri. The fundamental challenge lies in something called the Tsiolkovsky rocket equation, formulated by the Russian scientist Konstantin Tsiolkovsky in 1903. This equation defines the relationship between a rocket's mass, its exhaust velocity, and the final speed it can achieve. It's an elegant piece of physics, but it reveals some sobering constraints. The rocket equation tells us that achieving high velocities requires exponentially more fuel. If you want to double your spacecraft's final speed, you don't just need twice as much fuel. You need vastly more, depending on your engine's efficiency. To reach truly high velocities, you need to carry astronomical quantities of propellant, but here's where the cruel mathematics kicks in. Every kilogram of fuel you add to your rocket is mass that must be accelerated along with everything else. More fuel requires a larger fuel tank, which requires more structural mass, which requires even more fuel to accelerate the larger structure. It's a vicious cycle that grows exponentially with each increment of desired velocity. Imagine trying to pack for a trip where you have to carry not just your clothes and supplies, but also all the gas your car will need for the entire journey. Now imagine that every extra gallon of gas requires a larger car to carry it, and that larger car needs even more gas to move its greater weight. This is the tyranny of the rocket equation. Ion engines represent a more elegant approach to the propulsion problem. Instead of burning chemical fuel, These engines accelerate charged particles to much higher velocities, often 10 to 20 times faster than chemical exhausts. Because they achieve higher exhaust velocities, they can reach greater final speeds while using less fuel. NASA's Dawn spacecraft used ion propulsion to visit the asteroids Vesta and Ceres, accomplishing a mission that would have been impossible with chemical rockets. Over its operational lifetime, Dawn's ion engine provided a total velocity change of more than 11 kilometers per second, far exceeding what any chemical rocket could achieve with the same fuel mass. But ion engines produce incredibly tiny amounts of thrust. Dawn's engine generated only 92 millinewtons of force, roughly equivalent to the weight of a piece of paper pressing on your hand. To accelerate a spacecraft to useful velocities, ion engines must operate continuously for months or years. This makes them perfect for unmanned probes that have time to gradually build up speed, but utterly inadequate for human missions where people need to reach their destination within their natural lifespans. Humans require food, water, air, and protection from radiation throughout their journey. Every additional month of travel time adds mass and complexity to the life support systems. Nuclear propulsion offers the promise of much higher performance. In nuclear thermal engines, a reactor heats hydrogen propellant to extremely high temperatures, then expels it at velocities much greater than chemical engines can achieve. The physics is sound. Nuclear reactions release millions of times more energy per unit mass than chemical reactions. The United States actually developed and tested nuclear rocket engines during the NERVA program in the 1960s and early 1970s. These engines successfully demonstrated the technology, achieving exhaust velocities roughly double that of chemical rockets. But even doubling efficiency isn't nearly enough to make interstellar travel practical. Nuclear engines could cut interstellar travel times from hundreds of thousands of years to tens of thousands of years, still far beyond human timescales. It's like improving a horse-drawn wagon to travel twice as fast when what you really need is a supersonic jet. Fusion propulsion, harnessing the same nuclear process that powers stars, represents the theoretical pinnacle of chemical-based propulsion. Fusion reactions could, in principle, provide enough energy to accelerate spacecraft to a significant fraction of light speed, perhaps 10 or 12%. Project Daedalus, a detailed study conducted by the British Interplanetary Society in the 1970s, designed a theoretical fusion-powered probe that could reach 12% of light speed. At that velocity, it could reach Proxima Centauri in about 35 years, finally bringing interstellar travel within something approaching a human timescale. But the Daedalus design required 50,000 tons of helium-3 fuel. Helium-3 is extremely rare on Earth, but more abundant in the atmospheres of gas giants like Jupiter. The project would require decades of mining operations in Jupiter's atmosphere, extracting this rare isotope and transporting it back to Earth, a massive industrial undertaking that would dwarf any project humans have ever attempted. Moreover, we still don't have controlled fusion technology. Despite decades of intensive research and billions of dollars in investment, fusion power remains perpetually 30 years away. The physics is well understood, but the engineering challenges of containing and controlling fusion reactions have proven extraordinarily difficult. Even more exotic propulsion concepts run into fundamental limits. Antimatter represents the ultimate energy source according to known physics. When matter and antimatter annihilate, they convert 100% of their mass into energy, as described by Einstein's famous ʻOumuamua. Antimatter rockets could theoretically achieve velocities approaching the speed of light, but producing antimatter requires enormous amounts of energy, and our current production capabilities are laughably inadequate. Creating just 1 gram of antimatter would cost approximately $62 trillion using current methods. To put that in perspective, $62 trillion is roughly the annual gross domestic product of the entire world. For 1 gram, about the mass of a paperclip. In the entire history of particle physics research, humanity has produced less than 20 nanograms of antimatter. That's 20 billionths of a gram. But even assuming unlimited antimatter fuel, even assuming perfect propulsion technology that could accelerate spacecraft to 90% of light speed, we encounter other fundamental physical constraints that no engineering can overcome. As objects approach light speed, their kinetic energy increases dramatically. The energy required to accelerate a spacecraft grows exponentially as velocity approaches the cosmic speed limit of 300,000 kilometers per second. Reaching 90% of light speed would require energy equivalent to completely annihilating several mountains worth of matter. And at such enormous velocities, even the near vacuum of interstellar space becomes a hazard. Interstellar space isn't perfectly empty. It contains roughly 1 atom per cubic centimeter, along with tiny grains of dust. At normal velocities, this sparse matter poses no threat. But at relativistic speeds, these particles become deadly projectiles. A single grain of sand, no larger than what you might shake from your shoe after a day at the beach, would strike a spacecraft traveling at 90% of light speed with the kinetic energy of a nuclear weapon. The collision would release enough energy to vaporize the entire vehicle. Protecting against such impacts would require massive shielding, adding thousands of tons of mass to the spacecraft. But more mass means more energy required for acceleration, which brings us back to the exponential growth problem that has plagued every propulsion concept. This is why simply building faster engines doesn't solve the interstellar travel problem. Each increment of velocity doesn't just require more fuel. It multiplies every other challenge. Higher speeds demand stronger materials, better shielding, more sophisticated navigation systems, more robust life support. The engineering challenges don't just add up, they compound exponentially. The cruel irony is that the faster we try to go, the more difficult everything becomes. It's not like building a faster car where doubling the horsepower roughly doubles the top speed. In space, at the velocities required for interstellar travel, the laws of physics themselves become the enemy. We've reached a fundamental barrier where our ambitions as biological creatures, our desire to explore and expand across the cosmos within our brief lifespans, collide with the immutable laws that govern energy, mass, and velocity. No amount of engineering cleverness can change the fact that accelerating large masses to high velocities requires enormous amounts of energy, or that traveling at near light speeds transforms the universe itself into a hostile environment. Speed isn't the solution to interstellar travel. It's another problem that grows worse with every attempt to solve it. But even if we could somehow overcome the physics of propulsion, even if we could magically accelerate massive spacecraft to near-light speeds, we would still face an even more fundamental challenge. Human beings are extraordinarily fragile biological machines, exquisitely adapted for one specific environment, the surface of Earth. We are not built for the cosmos. We are built for a narrow band of conditions that exist only on our home planet, and every aspect of our biology reflects this limitation. Consider something as basic as breathing. Your brain, that 3-pound universe of consciousness reading these words right now, requires a constant supply of oxygen to function. Cut off that supply for just 4 minutes, and irreversible damage begins to occur. After 6 minutes without oxygen, brain death is likely. Your most essential organ, the seat of everything you think, feel, remember, and dream, can be permanently destroyed by a brief interruption in a process so automatic you rarely think about it. Each day you consume approximately 550 liters of oxygen just by existing. That's roughly the volume of a small closet filled with breathable gas that your body processes every 24 hours. On Earth, this oxygen is continuously renewed through the photosynthesis of plants and algae, a planetary life support system that has operated for billions of years. In space, every molecule of oxygen must be carried along or recycled from the carbon dioxide you exhale. There are no forests in the vacuum between stars, no vast oceans of oxygen-producing phytoplankton. Every breath depends entirely on the artificial life support systems functioning perfectly, day after day, year after year. Water presents another relentless demand. Your body requires at least 2 liters of clean water daily just to maintain basic cellular function. More during periods of physical exertion, more in warm environments, more when fighting illness. Over a year, that's roughly 700 liters per person, nearly 3/4 of a ton of water annually. The International Space Station achieves an impressive 93% water recycling efficiency, turning urine, sweat, and humidity from the air back into drinking water. But that remaining 7% must be replenished by cargo resupply missions from Earth. On an interstellar journey, there would be no resupply missions. Every drop lost would be gone forever. Perfect recycling, 100% efficiency, doesn't exist in any engineering system humans have ever built. There are always losses to evaporation, to chemical binding, to system malfunctions. Those small percentage losses become catastrophic failures when accumulated over decades. Food cannot be recycled at all in any meaningful sense. Unlike water and air, which can be processed back into usable forms, food represents a one-way consumption of mass and energy. The average person consumes roughly 700 kilograms of food per year. For a century-long journey, each passenger would require 70 tons of food, or a fully functional agricultural system capable of growing fresh produce in the confined environment of a spacecraft. Space agriculture sounds elegant in theory, but it demands everything that's precious aboard an interstellar vessel: space, energy, water, nutrients, and constant human attention. Plants need light, either from the sun, which becomes useless beyond a few astronomical units, or from artificial sources that drain power. They need soil or nutrient solutions, water for irrigation, carbon dioxide for photosynthesis, and careful monitoring to prevent disease. And beyond these basic metabolic needs, the space environment itself attacks human biology in ways that Earth dwellers rarely consider. Cosmic radiation bombards everything beyond our planet's protective magnetosphere. High-energy particles from supernovae, galactic cosmic rays, solar flares. These invisible bullets of energy penetrate spacecraft hulls and human tissue, damaging DNA and increasing cancer risk with every passing day. On Earth, our atmosphere and magnetic field deflect most of this radiation. In deep space, we're completely exposed. Astronauts on 6-month missions to the International Space Station, still within Earth's partial magnetic protection, already receive radiation doses equivalent to multiple full-body CT scans. On an interstellar journey lasting decades, crew members would accumulate radiation exposure levels far beyond anything humans have ever experienced. Radiation shielding requires mass, water, metal, or specialized polymers thick enough to absorb high-energy particles. But mass is the enemy of spacecraft design. Every kilogram of shielding is a kilogram that can't be used for fuel, life support, or living space. And remember our earlier discussion about propulsion. More mass requires exponentially more energy to accelerate. The absence of gravity creates its own cascade of biological problems. Without the constant downward pull that shaped our evolution, human bodies begin to deteriorate within days. Muscles atrophy rapidly. losing roughly 20% of their mass in just a few weeks. Bones lose density at a rate of about 1% per month as calcium leaches into the bloodstream. Astronauts on the International Space Station exercise for 2 hours daily using specialized equipment designed to simulate weight-bearing exercise. This intensive routine only slows the deterioration. It doesn't prevent it. After 6 months in microgravity, returning astronauts often need weeks or months of rehabilitation to regain their Earth-normal strength and bone density. Bodily fluids, no longer pulled downward by gravity, redistribute throughout the body. Blood and lymphatic fluid migrate toward the head, causing facial puffiness, increased pressure in the eyes, and persistent headaches. Many astronauts experience vision problems that can become permanent. Their eyeballs actually change shape under the altered pressure conditions. The immune system, evolved to function under Earth's gravitational field, weakens in microgravity. Astronauts become more susceptible to infections, allergies, and autoimmune responses. Wounds heal more slowly. Medications may not work as effectively. The very system that protects you from disease operates less efficiently when removed from its evolutionary context. Artificial gravity could theoretically solve these problems, but creating it requires massive rotating structures. The principle is straightforward. Spin a spacecraft, and centrifugal force pushes everything toward the outer rim, simulating gravity. But the engineering is anything but simple. Proposals for rotating spacecraft like the O'Neill cylinders, conceived in the 1970s, envision structures kilometers in diameter. Only at such enormous scales can rotation create comfortable artificial gravity without inducing motion sickness from the Coriolis effect. Building structures of this magnitude would require mining asteroids for raw materials and conducting construction projects in space that dwarf anything humans have ever attempted. But perhaps the most insidious challenge of interstellar travel isn't physical. It's psychological. Humans evolved as social creatures living in communities. We need interaction, variety, the ability to walk away from conflicts and form new relationships. Isolation and confinement drive people to psychological breaking points. The Biosphere 2 experiment in the 1990s offers a sobering preview of what might happen. 8 carefully selected individuals, all highly educated and motivated, were sealed inside a self-contained ecosystem for 2 years. Despite extensive preparation and psychological screening, the group developed serious conflicts. Factions formed. Communication broke down. The experiment had to be ended early due to social dysfunction. An interstellar journey would require not 8 people, but hundreds or thousands. Genetic diversity studies suggest that a minimum viable population to avoid inbreeding problems requires at least 98 individuals. More realistic estimates for maintaining a healthy, sustainable community range from 1,000 to 10,000 people. Supporting 1,000 people for a century would require infrastructure equivalent to a small, completely self-sufficient city. Not just life support systems, but manufacturing capabilities, hospitals, schools, entertainment, conflict resolution mechanisms, systems of governance. Everything needed for a thriving human community would need to be designed, built, and maintained within the confines of a spacecraft. No technology currently exists that could create such a system. We've never built a completely closed ecological system that can operate without external inputs for decades. Every attempt at creating self-sustaining habitats has required regular resupply and maintenance from the outside world. The International Space Station, humanity's most successful long-duration space habitat, requires regular cargo deliveries every few months. Replacement parts, fresh food, water, oxygen, fuel, scientific equipment, personal items for crew morale. The supply chain from Earth to orbit is constant and essential. Scale this up to an interstellar arc carrying thousands of people for centuries, and the engineering challenges become almost incomprehensible. Every component would need to be designed for unprecedented reliability. Backup systems would need backup systems. Manufacturing capabilities would need to exist for every critical component. The margin for error would approach zero, because there would be no possibility of rescue or resupply. We are biological creatures designed for a specific planetary environment, trying to venture into a realm that is fundamentally hostile to our form of life. Every breath we take, every heartbeat, every moment of consciousness depends on maintaining conditions that exist naturally only on Earth. The cosmos doesn't care about our biological needs. It operates according to physical laws that are indifferent to whether we live or die. And yet, faced with these seemingly insurmountable challenges, visionary thinkers have proposed a radical solution. If we can't travel fast enough within a single human lifetime, perhaps multiple generations could complete the journey. The generation ship represents one of the most audacious concepts in all of human imagination. A spacecraft so vast, so completely self-contained, that it could house an entire civilization for the centuries-long journey between stars. The original crew who departed Earth would never see their destination. Their great-great-grandchildren might be the first to glimpse the light of an alien sun. This isn't a new idea. As early as 1918, rocket pioneer Robert Goddard wrote about what he called the ultimate migration, humanity's response to the eventual death of our sun. In 1911, even before Goddard, the visionary Konstantin Tsiolkovsky imagined passengers traveling for generations aboard spacecraft that were essentially flying worlds. John Desmond Bernal, the brilliant British scientist, described massive spherical habitats in his 1929 work, The World, the Flesh and the Devil. These Bernal spheres would house thousands of people in artificial worlds that rotated to create gravity, complete with their own atmospheres, ecosystems, and societies. Project Daedalus, that ambitious British study from the 1970s we discussed earlier, envisioned a 54,000-ton spacecraft that could reach 12% of light speed. Even at that tremendous velocity, the journey to Proxima Centauri would take 50 years, requiring at least 2 generations aboard the vessel. The Ensman starship, proposed in 1964, painted a picture of a 600-meter-long vessel that could accommodate 200 people initially, with space designed for population growth over the decades of travel. These early passengers would establish families, raise children who knew no world but the interior of the ship, and gradually build a society adapted for life in the void between stars. Gerard O'Neill, the Princeton physicist who inspired a generation of space colonization enthusiasts, designed rotating cylindrical habitats 32 kilometers long that could house millions of people in Earth-like conditions. These massive structures would create their own weather patterns, complete with clouds and rain, artificial seasons, and vast landscapes that passengers could explore. More recently, Project Hyperion, initiated in 2011, has been studying the practical feasibility of generation ships using near-term technology. In 2024, design competitions asked engineering teams to propose concepts for 200-year journeys, resulting in detailed proposals for modular habitats, hydroponic agriculture systems, and recycling technologies that approach perfect efficiency. The mathematical requirements are sobering. A minimum population of 1,000 people has been established to ensure genetic diversity and social stability. Too few people and genetic bottlenecks become inevitable within a few generations. Inbreeding increases the risk of genetic disorders and reduces the population's ability to adapt to new challenges. But keeping the population manageable means capping it around 10,000 people. Large enough for diversity, small enough that resources remain controllable without overwhelming the life support systems. This population would need to remain stable for centuries, carefully managing birth rates, death rates, and resource consumption. Imagine what life would be like aboard such a vessel. Each generation would live and die, knowing only the metallic interior of their spacecraft. Children born in the third year of the journey would never see an open sky, never feel wind that wasn't artificially generated, never witness a sunset that wasn't painted on a dome. Those born aboard the ship would have no visceral understanding of concepts that seem fundamental to us. They would know up and down only through artificial gravity created by rotation. They might learn about oceans from recordings and textbooks, but they would never feel sand between their toes or hear waves crashing against a shore. As decades pass, the connection to Earth would inevitably fade. The original crew members' stories about blue skies and green forests would become legends passed down through oral tradition. Eventually, even video recordings might seem as mythical to shipborne generations as ancient stories seem to us. Language itself would begin to evolve in isolation. Cut off from the linguistic development happening on Earth, the ship's population would develop its own dialects, slang, and eventually perhaps entirely new grammatical structures. After several generations, the language spoken aboard the ship might become incomprehensible to Earth dwellers. Social structures would transform in ways impossible to predict. New religions might emerge based on the unique experiences of life in space. Different forms of government might develop, adapted to the confined environment and shared destiny of the ship's population. Cultural values would shift as generations adapted to their artificial world. These changes wouldn't necessarily be problems. They might represent natural human adaptation to a new environment. But they highlight how profoundly the journey would alter the very humanity of the passengers. Internal conflicts represent perhaps the greatest threat to a generation ship's survival. Unlike conflicts on Earth, where unhappy populations can migrate or establish new nations, the ship's passengers would be trapped together for centuries. A civil war, a religious schism, or even persistent social tensions could be catastrophic. Mutinies aboard such a vessel wouldn't just change leadership, they could doom everyone aboard. If one faction gained control of life support systems, or if sabotage damaged critical infrastructure, there would be no possibility of rescue or escape. The ship represents a single point of failure for the entire human population aboard. Technical maintenance becomes another generational challenge that compounds over time. Complex systems require constant upkeep, replacement of worn components, and occasional major overhauls. The technical knowledge to maintain these systems must be preserved and transmitted across generations without degradation. Consider how quickly technical knowledge can be lost even in our connected world. We've already forgotten how to build Saturn V rockets. The institutional knowledge, the specialized manufacturing techniques, the engineering shortcuts learned through experience. Now imagine trying to preserve far more complex technical knowledge across centuries, with no possibility of outside help. Every critical system would need multiple backups, and the crew would need the capability to manufacture replacement parts for everything from computer processors to air recycling filters. The ship would need to be not just a habitat, but a complete industrial civilization capable of producing everything necessary for survival. But perhaps the most profound challenge is motivational. The original crew volunteers for a mission to the stars, driven by exploration, adventure, or dedication to humanity's future. But what motivates their great-great-grandchildren, who never chose this life, to continue maintaining systems for a destination they've never seen? After 10 or 15 generations, the destination planet becomes an abstract concept. None of the current passengers would have ever met anyone who remembers Earth. The mission becomes a promise made by long-dead ancestors to reach a world that exists only in historical records. A 250-year journey represents 10 complete human generations living and dying successively aboard the vessel. A 1,000-year journey which might be necessary for more distant destinations, would require 40 consecutive generations to maintain knowledge, purpose, and social cohesion. Think about how much human civilization has changed in the past 1,000 years. Medieval Europe bears almost no resemblance to modern society. Languages, religions, political systems, technology, social structures, everything has transformed beyond recognition. The expectation that a ship's society would remain stable and mission-focused for millennia ignores the fundamental dynamism of human culture. Historical examples of isolated communities show how quickly social systems can diverge from their origins. Island populations develop unique cultures within generations. Australian Aboriginal populations, separated from other human groups for tens of thousands of years, developed entirely distinct languages, religions, and social structures. A generation ship would be the ultimate isolated community, with no possibility of cultural exchange or renewal from outside sources. The pressures of confined living, limited resources, and shared destiny would create social dynamics unlike anything in human history. The generation ship concept theoretically solves the problem of distance and time, but it introduces social, psychological, and technical problems that may be even more intractable than the physics of interstellar propulsion. We're asking thousands of people to dedicate not just their own lives, but the lives of their children and grandchildren to a goal that none of them will live to see achieved. But what if we could solve these problems through technology? What if we could engineer our way around the fundamental constraints of biology and time? Let me paint you a picture of technological perfection. Imagine a spacecraft equipped with fusion propulsion so advanced, so efficient, that it could accelerate continuously until reaching 10% of the speed of light. At that tremendous velocity, the journey to Proxima Centauri would require just 42 years. This miraculous vessel would be protected by deflector shields, force fields that could sweep aside interstellar dust and deflect the deadly radiation that particles become at such enormous speeds. Artificial gravity generated by the ship's rotation would perfectly simulate Earth's gravitational pull, eliminating muscle atrophy and bone density loss. Crew members could live in comfort, their bodies experiencing the same conditions they evolved for. The ship's recycling systems would achieve 99.9% efficiency. Nearly perfect closed loops that would transform waste back into air, water, and nutrients with almost no losses. Hydroponic gardens would provide fresh food continuously using artificial sunlight and recycled nutrients to grow vegetables and grains in perfect abundance. Advanced medical technology would allow for hibernation or suspended animation, dramatically reducing the aging process during the long journey. Passengers could be frozen in perfect cryopreservation, their biological processes slowed to nearly zero, awakening decades later with minimal cellular damage. Even in this optimistic scenario, even with technology that borders on magic, the fundamental challenge remains. A passenger who entered hibernation at age 20 would emerge at Proxima Centauri at age 62. They would have lost 42 years of active life. 4 decades of experiences, relationships, and growth sacrificed for a journey to another star. The personal cost extends beyond the individual traveler. Friends and family left behind on Earth would age normally during those 42 years. Parents might die of old age. Children would grow up and have children of their own. By the time the traveler could send a message home, a message that would take 4.2 years to cross the interstellar void, everyone they knew might have moved on, aged beyond recognition, or passed away entirely. Communication across interstellar distances creates its own form of isolation. Real-time conversation becomes impossible when each exchange requires years to complete. A question sent from Proxima Centauri would reach Earth 4.2 years later. The answer would take another 4.2 years to return. By the time explorers received replies to their messages, nearly a decade would have passed. Messages sent from the destination might arrive on Earth after their senders had already died. The delay creates a haunting disconnection, voices from the past arriving long after their speakers have become memories. At velocities approaching the speed of light, Einstein's relativity introduces additional complications that no amount of technology can overcome. Time itself behaves differently at extreme speeds. A spacecraft traveling at 90% of light speed would experience time dilation. Time would pass more slowly for the crew relative to observers on Earth. The numbers are startling. Crew members might experience a 20-year journey to a distant star while 40 years pass on Earth. Upon returning home, the travelers would discover a world that had aged twice as much as they had. Technology would have advanced beyond recognition. Society would have transformed. Everyone they left behind would be decades older, if still alive. This isn't science fiction speculation. Time dilation is a confirmed physical reality. Experiments with atomic clocks on fast-moving aircraft show measurable differences in elapsed time. Particles accelerated in laboratory colliders experience time at different rates depending on their velocity. Astronaut Sergei Krikalev, who spent 803 days aboard various space stations orbiting Earth at 27,000 kilometers per hour, aged about 20 milliseconds less than he would have on Earth's surface. At interstellar velocities, these effects would be amplified dramatically. Space travelers would become temporal exiles, disconnected not just by distance, but by the flow of time itself. Even assuming perfect technology, physics imposes absolute limits that no engineering can circumvent. The speed of light represents a universal constant, 299,792,458 meters per second, that cannot be exceeded by any object with mass. This isn't a technological limitation waiting to be overcome. It's a fundamental feature of how space and time are woven together. Accelerating a spacecraft to 90% of light speed would require energy equivalent to completely annihilating the mass of entire mountains. But that's only half the energy budget. The ship would need identical amounts of energy to decelerate upon arrival. The fuel requirements become so enormous that the spacecraft would need to carry fuel masses exceeding those of asteroids. And here we encounter the same tyrannical mathematics that plague all propulsion systems. The fuel has mass, and that mass requires additional fuel to accelerate. The energy requirements grow exponentially with desired velocity. At some point, the fuel needed to carry the fuel needed to carry the fuel becomes absurd. Perfect technology cannot eliminate fundamental physics. The laws of thermodynamics, the principles of relativity, the conservation of energy. These aren't temporary inconveniences waiting for clever engineers to solve. They are the underlying rules that govern how reality operates. Assuming propulsion systems that ignore energy costs is scientific fantasy, not rigorous extrapolation. It's like assuming we could fly by ignoring gravity, appealing in imagination, but useless for actual planning. Even traveling at near-light speeds, the galaxy remains fundamentally inaccessible within human timescales. The Andromeda galaxy lies 2.5 million light-years away. At 90% of light speed, the journey would require nearly 3 million years. The center of our own galaxy, with its dense collection of stars and exotic objects, sits 26,000 light-years distant, still requiring millennia of travel time. The observable universe extends roughly 93 billion light-years in every direction. This scale is so vast that even light, traveling for the entire age of the universe, has barely begun to sample its contents. No conceivable propulsion system could make such distances accessible to creatures that live for decades. Perfect technology cannot change the fundamental mismatch between human time scales and cosmic distances. We live our lives in decades, but the universe operates across eons. Stars burn for billions of years. Galaxies evolve over cosmic time. Light from distant quasars began its journey toward us when the universe was young. The final bottleneck isn't engineering, it's biology. We are ephemeral creatures in an eternal cosmos, mayflies trying to comprehend geological time. Our consciousness, our dreams, our ambitions all unfold within the narrow window of a human lifetime. The universe extends far beyond those boundaries, both spatially and temporally. No amount of technological advancement can reconcile this fundamental incompatibility between the scales of human experience and cosmic reality. We can build faster ships, more efficient engines, better life support systems, but we cannot extend human consciousness to cosmic timescales or compress cosmic distances to human proportions. The most perfect spacecraft imaginable would still carry mortal passengers on journeys measured in decades or centuries. Even perfect technology cannot make us immortal, cannot make interstellar space small, cannot make distant stars near. And this brings us to perhaps the most fundamental constraint of all, the brief flicker of human existence itself. The average human lifespan in developed countries with access to modern medicine is approximately 80 years. 80 years. Let that number settle in your mind for a moment. In the grand scheme of cosmic time, 80 years represents less than a heartbeat. Yet, within those 8 decades, we somehow expect to fit entire lifetimes of experience, learning, love, achievement, and perhaps, just perhaps, a journey to the stars. Jeanne Calment, the longest-lived person in verified human history, reached 122 years before her death in 1997. She was born when the American Civil War was still a recent memory, when horses and carriages filled city streets, when electric lighting was a novelty available only to the wealthy. She lived to see automobiles, airplanes, radio, television, computers, and the dawn of the Internet age. Her extraordinary lifespan represents the absolute upper limit of what we know to be possible for human longevity. Medical researchers studying the fundamental biology of aging suggest that even under ideal conditions, the human lifespan has a theoretical maximum somewhere between 125 and 130 years. This isn't a technological limitation that better medicine might overcome. It appears to be a fundamental constraint built into our cellular biology. Aging is a biological process written into our DNA. Telomeres, the protective caps on our chromosomes, shorten with each cell division until cells can no longer reproduce. DNA accumulates damage from radiation, chemical exposure, and simple metabolic processes. Proteins fold incorrectly and accumulate in our tissues. Even if we eliminated every disease, every accident, every external cause of death, our cells would eventually stop dividing, our organs would gradually fail, and we would die of old age. Some optimistic scientists believe that genetic interventions, stem cell therapies, or other biotechnologies might eventually extend human life to 200 years or perhaps more. But such extensions require understanding the fundamental mechanisms of aging, mechanisms that remain partially mysterious even after decades of intensive research. We don't yet know if aging is a problem to be solved or an inevitable consequence of complex biological systems. While we debate the theoretical limits of human longevity, interstellar journeys demand time measured in decades, centuries, or millennia. Even if we could routinely live to 200 years, doubling our current maximum lifespan, a traveler would still age significantly during even the most optimistic interstellar voyage. Consider our perfect fusion spacecraft reaching 10% of light speed, completing the journey to Proxima Centauri in 42 years. A traveler who departed at age 20 would arrive at 62, having spent more than half their adult life in transit. But that's only half the story. Returning to Earth would require another 42 years. The round trip would consume 84 years of life. Such a traveler would depart Earth as a young adult and return as a centenarian, having spent 8 decades of their precious finite existence traveling through empty space. They would arrive at their destination too old for the physical demands of colonizing a new world, too elderly to adapt to alien environments, too near the end of their biological lifespan to contribute meaningfully to establishing human presence on another planet. Suspended animation offers a theoretical solution, pausing biological processes during the journey to prevent aging. But despite decades of research and countless science fiction stories, true suspended animation remains purely speculative. The hibernation observed in some mammals reduces metabolic rate and activity, but it doesn't stop aging entirely. Cells continue to degrade slowly even in hibernating bears or ground squirrels. Cryopreservation. Freezing biological tissue can halt cellular processes, but current methods cause irreversible damage. Ice crystals form inside cells, rupturing delicate membranes and destroying vital structures. No mammal larger than a small insect has ever been successfully frozen and revived without significant tissue damage. Vitrification, a process that turns biological tissue into a glass-like state without forming ice crystals, avoids some of these problems. But reversing the vitrification process without damaging cells remains technically impossible with current technology. We can preserve tissue in a glass-like state, but we cannot yet restore it to living, functional biology. Even more speculative concepts like uploading human consciousness to computers remain firmly in the realm of science fiction. Consciousness emerges from the incredibly complex physical processes of the brain. The precise patterns of electrical activity, chemical signaling, and structural connections among billions of neurons. Simply copying these patterns into a computer wouldn't preserve personal identity. It would create a copy while the original consciousness remained trapped in mortal flesh. The fundamental challenge persists. Even assuming miraculous future technologies, even imagining breakthroughs that seem impossible today, time itself remains an obstacle. Interstellar journeys require time spans that exceed human generations. The distances are so vast that no conceivable technology can compress them into human-scale timeframes. No technology can eliminate the physical reality that Proxima Centauri lies 40 trillion kilometers away. No engineering breakthrough can change the fact that light, the fastest thing in the universe, requires 4.2 years to cross that distance. For human travelers to reach other stars in reasonable time, we would need to travel faster than light itself. But Einstein's special relativity absolutely prohibits objects with mass from reaching or exceeding the speed of light. As an object approaches light speed, its mass increases toward infinity, requiring infinite energy to accelerate it further. This isn't a technological challenge waiting for clever engineers to solve. It's a fundamental feature of how space and time work. The universe operates according to rules: maximum velocity, conservation of energy, the inexorable increase of entropy. These aren't arbitrary limitations imposed by nature out of spite. They're the underlying mathematical relationships that make physical reality possible. We exist within these constraints. We cannot simply ignore them when they become inconvenient. 80 years seems like enough time for a rich, meaningful life. Within those decades, you can build careers, form deep relationships, raise children who will carry your values into the future, create art that outlasts your physical existence, contribute to the accumulated knowledge and wisdom of our species. You can experience love, friendship, wonder, achievement, and the deep satisfaction that comes from a life well lived. But 80 years, even 120 or 200 years, is absolutely insufficient for exploring a cosmos that extends across billions of light years. This isn't a failure of technology or imagination. It's a fundamental incompatibility between the scales of human experience and cosmic reality. We are creatures designed to live for decades on a planet that has existed for billions of years, orbiting a star that will burn for 10 billion years in a galaxy that has been slowly rotating for over 13 billion years. Our entire species, from the first primitive hominids to the most advanced spacefaring civilizations we might become, represents a brief moment in cosmic time. The mismatch isn't accidental or correctable. It reflects the basic architecture of reality, where complex structures like living beings can exist only briefly against the vast backdrop of cosmic time and space. Stars burn for eons, but the nuclear fusion that powers them destroys the very complexity that makes life possible. Planets remain stable for billions of years, but they're rare islands of habitability in a universe that's mostly empty space. Consciousness itself, the awareness reading these words right now, represents an extraordinary and temporary organization of matter and energy. Your thoughts, memories, and sense of self emerge from billions of neurons firing in precise patterns, a biological machine that maintains itself for a few decades before entropy inevitably claims it. We dream of exploring the cosmos because we are conscious beings capable of wonder and curiosity. But we remain bound by the same physical laws that govern everything else in the universe. We cannot transcend our biology through technology alone, cannot compress cosmic distances through engineering, cannot extend our brief lifespans to cosmic scales through medical intervention. The stars will remain beyond our reach not because we lack sufficiently advanced rockets, but because we are ephemeral creatures in an eternal cosmos. And yet, perhaps we're approaching this challenge from the wrong direction entirely. Maybe interstellar exploration doesn't require human beings to physically travel through the dark void between stars. Robotic probes can journey for centuries without needing food, water, air, artificial gravity, or social interaction. They don't suffer from muscle atrophy, bone density loss, or the psychological strain of isolation. They don't require the massive life support infrastructure that makes human spaceflight so enormously complex and energy-intensive. Voyager 1 has been functioning for 47 years, powered by the slow radioactive decay of plutonium. This remarkable machine launched during the Carter administration and continues transmitting data as we speak, despite being farther from Earth than any human-made object has ever traveled. Engineers hope it will continue operating until 2036, when its nuclear power source finally depletes after 6 decades of continuous operation. Think about that achievement for a moment. A machine built with 1970s technology has been operating flawlessly in the harsh environment of space for longer than many people have been alive. It has endured cosmic radiation, extreme temperatures, micrometeorite impacts, and the gradual degradation that affects all electronic systems. Yet it continues its mission, faithfully sending data across billions of kilometers of space. Robots don't experience boredom during the long years of interstellar cruise. They don't suffer loneliness or homesickness. They don't age or fall ill. They don't need entertainment, social contact, or psychological support. For missions lasting centuries, mechanical explorers seem ideally suited to the task. They could sleep through the journey in powered-down mode, awakening only when they reach their destination, ready to begin scientific observations with fresh instruments and undamaged systems. Modern robotic missions have already demonstrated extraordinary capabilities. The Mars rovers Spirit, Opportunity, and Curiosity have operated far beyond their planned mission durations, conducting detailed geological surveys of the Martian surface. The Cassini spacecraft spent 13 years studying Saturn and its moons, revealing the complex chemistry of Titan's atmosphere and the potential for life in Enceladus's subsurface ocean. The Hubble Space Telescope has been humanity's eye on the cosmos for over 3 decades, capturing images that have revolutionized our understanding of the universe. For interstellar exploration, robotic probes offer compelling advantages. They can be built to withstand the radiation environment of deep space without the complex shielding required for human survival. They can operate at extremely cold temperatures that would kill biological organisms. They can be designed for specific scientific missions without the compromises required to support human life. But here's what robotic exploration cannot provide: the human experience of wonder. A robotic probe might photograph an alien sunset, measure the spectral composition of its light, analyze atmospheric conditions, and transmit detailed scientific data back to Earth. But it cannot feel awe at the beauty of light filtering through an alien sky. It cannot experience the emotional impact of seeing a new world for the first time, cannot feel the profound significance of standing where no human has ever stood. There's something fundamentally different between experiencing a place and merely collecting data about it. When you stand at the edge of the Grand Canyon, you don't just observe geological formations. You feel the vastness, the ancient timescales written in rock layers, the humbling sense of your own smallness against the magnitude of natural forces. A camera can capture the visual information, but it cannot replicate the emotional and spiritual impact of being present in that moment. Robotic exploration without human explorers becomes data collection. Scientifically valuable, certainly, but somehow empty of human meaning. When we dream of exploring Mars, we don't envision sending better rovers with more sophisticated instruments. We dream of walking across Martian plains ourselves, feeling alien soil crunch beneath our boots, breathing recycled air inside our helmets, while gazing at Earth as a blue dot in the Martian sky. The question becomes, what's the purpose of colonizing the stars if humans never experience the worlds our machines discover? If every habitable planet, every alien vista, every cosmic phenomenon remains accessible only through the electronic senses of robotic surrogates, do we truly explore the cosmos or merely catalog it from afar? Some visionaries propose more ambitious solutions that attempt to bridge this gap between mechanical capability and human experience. Seed ships might carry not living humans, but the genetic information and technological infrastructure to create humans at the destination. These vessels would transport frozen embryos or sophisticated biological printers capable of synthesizing human beings from stored genetic data. Imagine a robotic probe arriving at Proxima Centauri after centuries of travel, then using its cargo of genetic templates and artificial wombs to produce the first generation of humans on an alien world. These children would be born under foreign stars, raised by artificial intelligence systems programmed to teach them human language, culture, and values. In theory, this approach could establish human presence on distant worlds without requiring living humans to survive the journey. But consider what those humans would actually be. They would be orphans in the deepest sense, born without parents, without grandparents, without the accumulated cultural wisdom that passes from generation to generation through direct human contact. They might be genetically human, but culturally they would be aliens, raised by machines that understand human knowledge but not human meaning. These artificially created humans would grow up knowing Earth only through historical records and digital archives. They would speak human languages learned from computers, practice human traditions taught by robots, inherit human values filtered through artificial intelligence. Would they truly be human in any meaningful sense? Or would they be something new? Human-shaped beings adapted to a technological rather than biological heritage. The absence of human cultural transmission would create profound gaps in their understanding. So much of what makes us human isn't encoded in our genes, but passed down through countless generations of shared experience. The way we laugh at certain jokes, the emotional weight we attach to particular rituals, the intuitive understanding of social dynamics, these aspects of humanity emerge from our collective cultural evolution. Children raised entirely by machines might develop language skills and technical knowledge, but would they understand poetry? Would they feel the emotional resonance of music? Would they comprehend the complex web of motivations, fears, and dreams that drive human behavior? They might be human in form, but alien in spirit. Remote operation offers another theoretical approach, but it immediately encounters the fundamental constraint of interstellar distances. Commands sent to a probe orbiting Proxima Centauri would take 4.2 years to arrive. The probe's response would take another 4.2 years to return to Earth. Every decision would require 8 years of waiting, making real-time exploration impossible. Even operating rovers on Mars frustrate scientists with communication delays of 20 minutes each way. Mission controllers must plan every movement hours in advance, unable to respond immediately when interesting discoveries emerge or when equipment malfunctions threaten the mission. Scientists often describe the agony of watching rover cameras reveal tantalizing glimpses of potentially important features, then having to wait hours before they can command the rover to investigate. Extend that delay to 8 years, and exploration becomes painfully slow, reduced to broad programmatic decisions rather than the moment-to-moment choices that define true exploration. The spontaneous curiosity that drives discovery, the sudden decision to examine an unusual rock, the instinct to look over the next hill, becomes impossible when every action requires nearly a decade of round-trip communication. Advanced artificial intelligence might solve the communication delay problem by making decisions autonomously without waiting for instructions from Earth. But creating truly autonomous AI capable of conducting sophisticated scientific research remains an unsolved challenge. Current AI systems can process enormous amounts of data and recognize complex patterns, but they don't understand meaning in the way humans do. An AI might identify an unusual rock formation and correctly classify it according to its programming. But it cannot feel excitement at a potentially revolutionary discovery, cannot intuitively sense when something deserves deeper investigation, cannot experience the spark of insight that leads to breakthrough understanding. AI processes information, it doesn't comprehend significance. The most profound scientific discoveries often come not from following predetermined protocols, but from recognizing unexpected patterns, asking unconventional questions, or pursuing seemingly irrelevant curiosities. Human scientists possess intuition, creativity, and the ability to see connections that weren't explicitly programmed. They can look at data and suddenly realize its implications extend far beyond the original hypothesis. The concept of uploading human consciousness to digital form, creating robotic explorers with human minds, remains firmly in the realm of science fiction. Neuroscience doesn't yet understand consciousness well enough to even theoretically copy it to artificial systems. We know that consciousness emerges from the incredibly complex interactions of billions of neurons, but we don't know how those interactions create subjective experience. Even if consciousness uploading became possible, fundamental questions would remain about identity and continuity. The uploaded person would be a copy, not a continuation of the original mind. The biological human would remain on Earth, while their digital duplicate explored the stars. Would that digital copy truly be the same person, or simply a very sophisticated simulation with identical memories and personality patterns? Virtual reality technology might allow humans to experience interstellar exploration through robotic surrogates equipped with sophisticated sensors. Instead of simply viewing data transmitted from distant probes, operators could experience immersive virtual environments that simulate walking on alien worlds. Advanced haptic feedback could provide the sensation of touching alien materials, feeling alien atmospheres, experiencing the reduced gravity of distant planets. But this approach still faces the 8-year communication delay that makes real-time interaction impossible. The most immersive virtual reality system would still be limited to experiencing pre-recorded sequences or following predetermined exploration routes. The spontaneous decision to climb a hill or investigate an anomaly would require years of waiting for the probe to respond. Perhaps future generations will accept that interstellar exploration belongs to machines rather than humans. They might find satisfaction in the knowledge that robotic ambassadors are extending human presence to other star systems, even if no human will ever set foot on those distant worlds. Scientific discovery might become enough to satisfy our species' exploratory drive. But accepting such limitations means abandoning one of humanity's defining characteristics. Exploration is written into our DNA, encoded in behaviors that drove our ancestors to leave Africa, populate every continent, cross dangerous oceans in wooden boats, and ultimately reach for the moon. ʻOumuamua. We are the species that cannot resist going beyond the next horizon, that feels compelled to see what lies just out of sight. Throughout history, the most meaningful exploration has required human presence. Lewis and Clark didn't just map the American West. They experienced it directly, adapting to its challenges, learning from its native inhabitants, bringing back not just geographic data, but stories infused with human meaning. The Apollo astronauts didn't just collect moon rocks. They stood in alien landscapes and looked back at Earth with human eyes, experiencing a perspective shift that changed how our entire species sees our planet. Their words about Earth's fragility and beauty, their descriptions of the profound silence of space, their emotional reactions to seeing our world as a small blue marble. These human experiences resonated with people worldwide in ways that purely scientific data never could. The famous Earthrise photograph moved millions not because of its technical quality, but because it was taken by human eyes, framed by human consciousness aware of its significance. Stopping human exploration at the edge of our solar system, accepting that we can send only machines to represent us among the stars, feels like a fundamental surrender. It means acknowledging that we are destined to remain a single-planet species, forever confined to the small blue world that gave us birth. Yet perhaps that acceptance represents wisdom rather than defeat. Perhaps recognizing that the cosmos is too vast for creatures as small and brief as ourselves isn't failure, but maturity. Perhaps understanding our limitations is the first step toward finding meaning within them. To truly grasp our place in this vast cosmos, we need to step back and consider the immense timeline that brought us to this moment. The universe itself is 13.8 billion years old, born in the Big Bang that created space, time, matter, and energy all at once. In those first moments, the entire observable universe was smaller than an atom, then expanded and cooled, allowing the formation of the first particles, the first atoms, and eventually the first stars. Our Earth formed 6 billion years ago from the slow accretion of cosmic dust and debris orbiting a young sun. For its first billion years, Earth was a hellish world of volcanic activity, asteroid bombardment, and gradually cooling temperatures. Life emerged approximately 3.8 billion years ago. Simple, single-celled organisms that dominated the planet for eons, slowly learning to harness sunlight through photosynthesis and filling the atmosphere with oxygen. For most of Earth's history, life remained microscopic. Complex multicellular animals didn't appear until about 600 million years ago, when something called the Cambrian explosion led to a rapid diversification of life forms. Even then, it took hundreds of millions more years for life to colonize the land, develop complex ecosystems, and evolve the incredible diversity of species we see today. Dinosaurs ruled Earth for 165 million years, a span of time so vast that it's longer than the entire period from their extinction to today. These magnificent creatures dominated every continent, evolved into countless species, and seemed destined to reign forever. Then a 6-mile-wide asteroid struck the Yucatan Peninsula 66 million years ago, ending their evolutionary dynasty in a geological instant. Primates emerged only 60 million years ago, taking advantage of the ecological niches left vacant by the dinosaurs' demise. Our hominid ancestors appeared just 7 million years ago, yesterday in geological time. Modern humans, Homo sapiens, have existed for only 300,000 years. Everything we consider civilization, agriculture, cities, writing, art, science, has existed for merely 10,000 years. The entire span of recorded human history, from the first Sumerian cuneiform tablets to the smartphone in your pocket, represents less than 0.03% of Earth's history. The Industrial Age, which transformed human society and gave us the technology to reach for the stars, is only 250 years old. The Space Age, humanity's first tentative steps beyond our home planet, has existed for just 60 years. In cosmic terms, our technological civilization emerged moments ago. Individual human lives unfold over decades while stars burn steadily for billions of years. Our sun, that familiar disk of light that has illuminated every human story ever told, will continue burning for another 10 billion years before expanding into a red giant that will consume Mercury, Venus, and possibly Earth. Long after our species and everything we've ever built has turned to dust, the sun will still be shining. Red dwarf stars like Proxima Centauri burn their nuclear fuel so slowly that they'll continue shining for trillions of years, longer than the current age of the universe. Galaxies will continue their stately dance, colliding and merging, forming new stars and planets for hundreds of billions of years into the future. Humanity could be extinct long before our sun even begins to show signs of aging. Species typically last only a few million years before evolving into something else or vanishing entirely. Even if we survive, we'll evolve beyond recognition within a few million years. The humans of the distant future, if they exist at all, might be as different from us as we are from early primates. On the timeline of cosmic history, individual human experience is literally a blink of an eye. Your entire life, from birth to death, represents an infinitesimal fraction of the universe's story. Every emotion you've ever felt, every relationship you've treasured, every achievement you've celebrated, all of it unfolds within a time frame that's essentially zero when measured against cosmic scales. But here's the remarkable thing. Within that blink, you experience love, joy, curiosity, wonder, and the profound satisfaction of understanding. Within those brief decades, you can form deep connections with other conscious beings, create beauty that transcends your individual existence, and contribute to humanity's growing comprehension of the cosmos. Our limitation doesn't diminish our significance, it defines it. Human life is precious precisely because it's brief and singular. Each consciousness that emerges represents a unique perspective on reality, a temporary organizing of matter and energy into awareness capable of contemplating its own existence. We will never colonize the galaxy, never establish cities among distant stars, never walk on the shores of alien oceans, but we can contemplate the galaxy's majesty and understand our place within it. We can measure its dimensions, study its evolution, and comprehend the physical laws that govern its behavior. Science allows us to transcend our physical limitations through understanding. We know the cosmos without visiting it entirely. Our telescopes reveal galaxies billions of light years away, showing us light that began its journey when the universe was young. When you look at the Andromeda galaxy through a telescope, you're seeing light that left those distant stars 2.5 million years ago, long before humans existed. We are privileged observers, consciousness somehow emerging from the cosmos and becoming capable of comprehending the very universe that created us. It's a profound mystery how matter organized into patterns complex enough to produce awareness, thought, and wonder. We don't understand consciousness well enough to explain how it arises, but we know it's precious and rare. Perhaps true exploration isn't about visiting places personally, but about understanding them deeply through careful scientific observation. Physicists have unraveled the secrets of black holes without ever approaching one directly. They've mapped the event horizon, calculated the physics of matter falling past the point of no return, and even captured images of these cosmic monsters using networks of telescopes around the globe. We understand stellar evolution by observing different stars at various stages of their development. We know how stars are born in nebular nurseries, how they burn hydrogen in their cores, how they eventually exhaust their fuel and either collapse or explode. We've never witnessed a complete stellar life cycle. It unfolds over millions or billions of years. But we comprehend the process by studying many stars frozen at different moments in their evolution. We've discovered thousands of exoplanets by studying the tiny oscillations of distant stars, detecting the gravitational wobbles caused by orbiting worlds. We know about planets thousands of light years away, worlds we'll never visit but whose existence we can confirm and whose properties we can measure. Physical limitations force creativity, and often these indirect methods reveal truths that direct exploration might never uncover. We've learned more about the universe through telescopes than we ever could by traveling to distant objects. The Hubble Space Telescope has shown us galaxies as they were billions of years ago, cosmic archaeology that reveals the universe's history. Accepting that we are planetary creatures isn't defeat. It's recognizing the reality of our existence. Earth is our home, a blue oasis suspended in the cosmic dark. It's the only world in the known universe that harbors life, the only place where consciousness has emerged to contemplate its own existence. Our planet is fragile, a delicate balance of atmosphere, temperature, and chemistry that maintains the conditions necessary for life. The same space exploration that reveals the cosmos's vastness also shows us how special Earth is. Every other world we've studied, the freezing desert of Mars, the crushing hellscape of Venus, the icy moons of the outer planets, reminds us that habitable worlds are extraordinary exceptions. Perhaps our purpose isn't to colonize the stars, but to appreciate and protect the one world that made us possible. Perhaps our role is to be the universe's witnesses, the part of the cosmos that developed eyes and minds capable of seeing and understanding. We are the universe becoming aware of itself. Carl Sagan expressed this beautifully. We are made of star stuff, atoms forged in the nuclear furnaces of dying stars billions of years ago. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in stellar cores and scattered across space by supernova explosions. We are literally children of the cosmos, temporary arrangements of cosmic material that somehow learn to think and feel and wonder. In this vast and ancient universe, consciousness appears to be rare and precious. We may be alone or nearly alone in our ability to contemplate existence. That makes us extraordinarily valuable, not as conquerors of space, but as witnesses to its beauty. Our brief lives allow us to glimpse the eternal dance of matter and energy that surrounds us. We can watch the moon's phases, observe the planets' wanderings across the sky, and see galaxies spinning in the cosmic deep. We can measure the universe's expansion, study the formation of elements, and trace the evolution of complexity from simple particles to living beings. This is our form of cosmic exploration. Not through physical travel, but through understanding. We explore the universe with our minds, our instruments, and our imagination. We may never walk among the stars, but we can comprehend them. We may never visit other worlds, but we can discover them. In the end, perhaps being ephemeral creatures in an eternal cosmos is not a limitation, but a gift. Our brief existence gives weight to every moment, meaning to every connection, significance to every act of love or creation. We burn brightly for a short time, like candles in the cosmic dark, but in that burning, we create light, warmth, and beauty. The stars will outlive us by billions of years, but they cannot love, cannot wonder, cannot create meaning from existence. In our fragility and brevity, we possess something the eternal cosmos lacks. Consciousness capable of appreciation, minds able to find beauty in the vast dark, hearts that can love despite impermanence. We are creatures of a moment contemplating eternity, and in that contemplation we find our purpose and our peace. If you're still awake, it's because the content was really good. So take a moment, leave a like and subscribe to the channel. It helps a lot. And if you want to keep watching, just click on the video that's appearing right now. I'll see you there.